and we will continue our wonderful journey into Chapter 9. And so now we are going to do confidence intervals for means of populations, but now with two samples, okay? And so I'm just going to go ahead and throw the formula up for the confidence interval for means of means of populations with two samples, okay? And so this is our equation. So in the center we have, because we have two samples, you're going to have two x bars, and one is going to be x bar 1 and the other is x bar 2. Okay, and I'm going to put parentheses around that. And then plus or minus, we still have t star times, and we have a standard error, but it's an ugly formula. So anytime you have two samples, the formulas just get ugly, okay? So we have standard deviation of the first sample squared over n1, and so I'll label all of these things, okay? Okay, that's our equation. So let me just give you the labels for everything, okay? X bar 1 is sample mean, or let me just write mean of sample 1. Okay, so I hope that clears everything up here, okay? And t star is our critical value. Standard deviation of sample 1 and standard deviation of sample 2. Okay, and t star is our critical value from the table. And again, degrees of freedom is equal to n minus 1, but we have two n's, so we use the smaller of n1 and n2, okay? Is that okay with everybody? So in the center, we have this. This is our critical value. And this is our standard error. Okay, so the same pieces, it's just the equations, the way we calculate these things have changed, but the same line of thinking, line of reasoning that we've had before. Okay. Yes?
When you're saying use the smaller, and you're basically you're just using a smaller sample size.
Yeah,
Using one.
you're only using one of them, and you do n minus 1. Yeah, so you've got, because you have two n's, right? You've got sample 1 and you have sample 2, so you have two n's. Whichever one is the smaller n, you do that and you do n minus 1, and that's your degrees of freedom. Okay. Okay, so this is, so we have a question. Do people sleep different amounts on the weekend versus the weekday? Okay, and so we surveyed a lot of people, okay? 6,000, not 60,000, 6,007 people who slept, you know, and asked how much they slept on a weekday. Okay, and so the average of these 6,007 people was 500 minutes. Okay, with a standard deviation of 127 minutes. Okay, so 500 minutes is about 8 1/3 hours. Okay, 8 hours, 20 minutes. Okay, and then for the weekend, we surveyed 6,436 people. How much they slept on a weekend night, and the average average of these 6,436 was 556 minutes. With a standard deviation of 141 minutes. Okay. So let's just list off our data from our table. Okay, so or from the reading of the problem. So I have X bar 1, S1, N1, X bar 2, S2, and N2. Okay, so so just arbitrarily we've got to call one of these sample 1 and the other one sample 2. So let's call sample 1 the weekday, and sample 2 will be the weekend. Is that cool? All right, so tell me, what are X1, S1, X bar 1, S1, and N1?
6,007.
X bar 1 is 500, S1 is 127, and N1 is 6,007. Okay, X bar 2 is, okay, and S2 is sorry if my handwriting was bad. It's 141, and N2 is 6436. Okay. Is this okay? All right, and so now it's just a matter of plugging all of these things in. So I'm going to do 500 minus 556 plus or minus. We'll pick out the T star in a moment here. So actually, let's do that right now. So T star will have how many degrees of freedom? 6,006 degrees of freedom. Okay, and we go to our table, and we don't see 6,006. Okay, so the rule of thumb is generally, if you can't find the exact number, always round down, okay? If you can't find the exact number, always round down. And, you know, 6006, it's might as well be, we might as well just use the last row, but let's just round down. We'll follow our, just keep it simple. So we'll go to 95% probability. We don't see 6006, so we always round down, and so we're going to use 1.984, okay? But if you use 1.96, I won't get mad, okay? But 1.984, okay? So T star is 1.984, okay? So 6006 is not in the table. Okay, so round down to 100. Question?
When the confidence interval is like given, do we just assume it's 95%?
Oh yeah, sorry, it wasn't given. Yeah, assume 95%. That's going to be your most common value, but it should be given in the problem. I should have said something like 95% confidence. Another question.
6,006, how did you round that down
To 100?
to? Yeah.
Yeah, so it's just pick the number that's closest but not larger. Yeah, the highest number that's not bigger than the one you have. So in that case, it would be 100. So you're, yeah.
How does the 6006
Huh? So 6006 is, you have two ends, right? 6007 and 6436. And your degrees of freedom is always going to be n minus 1 using the smaller of the two ends.
Professor, I'm sorry, could you just show how you got that T star on the chart again?
So I'm going to the column 95%.
Right.
And then I'm going to use 100 degrees of freedom because that's the largest number I have that's not bigger than 6006. Yeah.
And how do we differentiate, because it wasn't given in the problem, the 95%? So
Yeah, I'm sorry. I should have written in the problem, make a 95% confidence interval. I should have written that. Okay. Now it's given. Okay. Make a 95% confidence interval. But yes. Okay. Is this okay? So now I'm going to plug in 1.984, and then I have to multiply it by this crazy thing. So S1 is 127. I square that, and I divide by N1 6007. And S2 is 141, and I square that, and I divide by 6436. Is that okay? Okay. Yes.
always 1 minus the n1?
It's always going to be n minus 1. It's not always n1. It's, you have two n's, right? We got 6007 and 6436. Okay? So whichever of these is smaller, we do n minus 1, that one. Okay? Yeah. All right, okay, so you're just going to punch this into your calculator. Okay, so 500 minus 556 gives me negative 56 plus or minus, and then you do all of this. In the interest of time, I'm going to just do it on the calculator, but if you're having issues with your calculator, I'm sorry, I'm not going to be able to say, like, this is what you need to do and all of that, okay? Just because we're going to run out of time if I did that. But I will tell you how I'm going to do it, okay? What I do is I figure out the inside part first, okay? So I'm gonna get this inside part, and I'm gonna do 127 squared divided by 6007 plus 141 squared divided by 6436. Okay? I calculate that, and then I'm going to take the square root of that. Square root of this number, so I get everything that's in, inside the square root here. Okay, and I get 2.40. So that's all of this. Okay, that's the entire this. So I have So right now I have negative 56 plus or minus 1.984 times 2 point, rounding off 2.403. Okay. Again, if you didn't catch all that, you can go on YouTube and watch this and just see how I typed it in. But basically, I like to do everything on the inside, take the square root of that, and then I do it. Okay, so now I'm going to multiply this by 1.984. And so I have negative 56 plus or minus 4. I'm just going to round off to 4.77. Okay? You can keep more decimals if you want, but for this, I'm just going to do negative 56 plus or minus 4.77. Okay, I'm going to copy all of this into the next slide so I can continue on here. Okay, and so my final answer is negative 56 plus or minus 4.77. So my upper bound and my lower bound will be negative 56 plus 4.77. I get negative 51.23. And then I do a minus, and I get negative 60.77. My upper and lower bounds. Okay, so here's the important part, the interpretation. Okay, I would write, I am 95% confident that, okay, now look, our confidence interval, we looked at weekday minus weekend, right? Because we did this negative 56, this is x bar 1 minus x bar 2, right? X bar 1 represents the weekday amount, and this represents the weekend amount. Okay? So I'm getting a negative amount. This is the weekday minus the weekend is negative, okay? So let's just think about what that means. Weekday minus the weekend ends up being negative, okay? So what does that mean? That means, do we sleep more or less during the weekday? Less, yes. Right? Okay, so I'm 95% confident that the average amount of sleep during the weekdays is between 51.23 minutes and 60.77 minutes less than the average amount of sleep during the weekends. Okay, because I got a negative 51.23 and a negative 60.77. So I'm 95% confident that the average amount of sleep during the weekdays is between 51 minutes and 60, basically 51 and 61 minutes less than the average amount of sleep during the weekends. Okay. And that's the average for everybody. So of course some people might be different, right? Some people might actually sleep more during the weekday versus the weekend or whatever. Okay, but but the average for everybody, we're 95% confident that it's, you know, this much less. Yes?
So that x1 minus x2 and the weekday minus weekend is negative or the same thing?
I'm sorry?
Is that x1 minus x2 and the weekday minus weekend the same thing?
Yes, yes. That's what I'm trying to say, is that the weekday we called x1, right? The sample 1. And then the weekend was group 2. All right. So do we have evidence that people sleep, on average, people sleep more on the weekend than on the weekday? Yes, and why is that? Because our entire interval does not include 0, right? 0 is not in the interval, so we have evidence that there is a difference. If 0 were in the interval, then that means 0, meaning no difference, is a possible answer. Okay, so here I'm going to write 0 is not within the interval. So we have evidence that there is a difference in the average amount slept. Between weekdays and weekends. Okay, and I'll write if 0 were in the interval, okay. On the other hand, if 0 were in the interval, we would not have evidence that there is a difference. Okay. Good? No? Alright, I'll give you a second to get everything written down. But I want to, well, conceptually, I know some of you guys are still writing, but conceptually, is this okay?
Yes.
Yes? Okay, okay. Yeah, question?
The interval you mean between 1.23 and 60.77?
Yes, yes. The, between the upper and lower bounds. Okay, so our entire interval is negative, so 0 is not in there. Okay. Okay. And now we're going to move into hypothesis testing. We're going to do hypothesis tests for means with 1 sample, and then hypothesis test for means with 2 samples. Okay, do we have all this down? Okay, good. All right, so do you guys remember how the hypothesis test stuff works for proportions? Kind of, okay. We always set up a null hypothesis and an alternative hypothesis, right? So we're going to have a null hypothesis and an alternative hypothesis. So in this case, because we're dealing with means, what do you think our null hypothesis looks like? Yeah, it's going to say mu is equal, the null hypothesis always has an equal sign, and it's going to be mu is equal to some number. So I'm just going to stick in a number here, 26, whatever, okay? But null hypothesis always has an equal sign. Okay, and you know, not necessarily 26, but some number, right? And so some number in that symbol, for some number it will be mu 0, okay? Just like for proportions we said p is equal to some number p0, here it's mu is equal to some number mu 0, okay? And then the alternative will be mu not equal, or mu greater than, or mu less than, whatever that number is, okay? Use the same number in the null hypothesis. Okay, just change to not equal, or greater than, or less than. Okay? And then so once we have our null and alternative hypotheses, we go through and we calculate a test statistic and a p-value, right? Same process. The test statistic our t is equal to x bar minus mu 0 divided by s over the square root of n. Okay? And this follows the same same form. Remember, I always said the test statistic is always in the form of what we observed minus expected from the null, right? Divided by the standard error. Okay, I'm hoping this kind of looks familiar, right, from last week. Same idea here. So last week it was p hat minus p0 over the standard error, whatever that thing was, square root of p0, 1 minus, you know, that thing. This time it's the same idea, except what comes from our sample? X bar. What's in our null hypothesis? Mu 0. What's our standard error? S over the square root of n. Okay, is that all right? Okay, so you get a test statistic. Okay, the weirdest thing here is that to get your p-value from the t-table, it's funny, okay? Getting your p-value from the t-table is very different than the way you use the z-table. Okay, and this is probably the biggest change to have to adapt to, but you do it a few times, you'll get comfortable. But the first couple times you see it, it's like, what are you doing? Okay, do it a few times, you'll get used to it. Okay, so look, getting the p-value from the t-table is very different from using the z-table. Okay. Okay, so this is what should happen. Okay, so if the alternative has greater than, then your test statistic, TS, should be positive. Okay, and if the alternative has less than, the test statistic should be negative, okay? If either of these statements are false, then you will not reject the null hypothesis, okay? The null hypothesis, okay? If your alternative HA has a not equal sign, then whether TS is positive or negative does not matter, okay? Okay, so here's the thing, okay? So to get your p-value, okay? Okay. Find the appropriate row for your degrees of freedom. Find the appropriate row in the table, T-table, for the degrees of freedom. Okay, for the DF. And then find which columns your test statistic fits between, okay, or which values the test statistic fits between. Okay, you may also find the test statistic might be greater than the largest number, or it could be smaller than the smallest number as well. Okay, so you want to just place it in between columns, or greater than the largest or smaller than the smallest. Okay, okay. TS could also be okay, and then I'm going to write the p-value is between the corresponding column headings. Okay, so I'll let you guys write all of this down. Well, I'm going to finish writing out the process for hypothesis testing, okay? And then we'll do some examples where we try to find the associated p-value, okay? Because I know this feels very abstract and it doesn't quite make sense yet, but we'll do a few examples of just finding the p-value first, and then I think you'll start to get the hang of it. If not tonight, as you do your work this week, okay? But I want to finish out the kind of the process of hypothesis testing, so it's all together in your notes. Okay, so I just want to make sure everybody's got this down. Okay, so I'm going to the, are we okay? All right, so I'm gonna go flip to the next slide. Okay, so your p-value, the resulting p-value will be in a range. But that's okay. Okay, you still make the same types of decisions, okay? Decisions based on the p-value. Okay, specifically, compare p-value to alpha. Which is stated in the problem or assumed to be 0.5 or 0.05. Okay. All right, and so this part should be a review, right? If the p-value is greater than alpha, what do?
We do not reject.
Yeah, do not reject what? The null hypothesis. Okay, do not reject the null hypothesis, and that means you do not have evidence to support the alternative. Okay. Same reasoning as before. If the p-value is less than alpha, then we reject the null hypothesis and we say you have evidence to support the alternative. Okay. So this should be familiar. Okay. Oh gosh, I forgot something. Okay. The resulting p-value will be in a range, but that's okay. Okay, so let me just insert this, and I apologize. Okay. So if the alternative has greater than or less than, okay, the p-value is between the column headings. And then if the alternative has a not equal sign, the p-value is between the column headings times 2. Okay, so even that should also seem kind of familiar-esque, right? Because last week, if the alternative had a not equal sign, you took the tail area and you multiplied it by 2. So here it's the same kind of idea, except you're dealing with the column headings, and it's do you multiply by 2 or not? Okay, sorry, I forgot to put that in there earlier. Okay. So I'll let you guys get this copied down, and then let's try an actual problem here. Okay, is this all right? Go back. All right, sure. Oh crap. August 18. Oh no, where did it go? Stats XL10. All right. Can I go now? We're good? Okay. All right, so let's say, all right, so at Domino's, I don't know, the medium pizza is how big? 12 inches? Something? 12 inches, okay? Or it's supposed to be, I should write. It's supposed to be 12 inches wide. Let's say you want to test if this is true, okay? So you buy, let's do somehow just a random selection of maybe 15 medium pizzas. And you measure how wide they are. Okay, so I don't know how you get a random sample of Domino's, but let's say you pick different locations and you order a medium pizza, whatever. Okay. So the average width of these 15 pizzas, man, I want to eat a pizza now. Of these 15 pizzas is, let's say, 11.72 inches. Man, they're cheating you out of a quarter of an inch, or a little bit more than that. Okay, maybe. All right. And then the standard deviation of these pizzas, pizza widths, are what? Is, let's say, 0.81 inches. Okay. So is this evidence that the average pizza size, average pizza width, is actually less than 12 inches? Right? You're buying a 12-inch medium pizza. Are they actually only giving you 11.72 inches? Do we have a class action lawsuit on our hands? What's going on? Okay, this is what we want to know. It's a very important question here, all right? So, we're going to do a hypothesis test, okay? So our null hypothesis is what? Mu, the average width of all pizzas, is equal to?
0.81.
No. We want to know, is it equal to 12 inches? Okay, is it equal to 12 inches? And then the alternative, we're wondering, are we getting less pizza than what I'm paying for, right? So we want to know, is the width actually less than 12 inches? Okay. All right, what is our data? Our data has N, X bar, and S. How many pizzas did I look at? 15. So N is 15. What was the average that I measured? 11.72, and the standard deviation was 0.81, right? Okay. So we're going to calculate my test statistic, which is X bar minus mu 0 divided by S over the square root of N. Okay, so I'm going to have 11.72 minus, what's mu 0? 12, the value that shows up in my null hypothesis, right? And I'm going to divide by S, which is 0.81, over the square root of N square root of 15. So when I do these calculations, I like to do the numerator first and I get negative 0.28. And then I figure out what my denominator is. 0.81 divided by the square root of 15. And I get 0.209. And so I do 0.28, negative 0.28 divided by 0.209, and I get negative 1.339. So far, so good? Okay, so I said if the alternative hypothesis has a less than sign, my test statistic should be negative, right? Okay, so that part is met, okay? HA has less than, and test statistic is negative, so we're good. Otherwise, we would say do not reject the null hypothesis right there, okay? If this number turned out to be positive, we would say do not reject the null hypothesis. But because it has a less than sign and the test statistic is negative, we go on. And so now we want to look this up in the t-table, okay? How many degrees of freedom do I have? Degrees of freedom is n minus 1. So I have 14 degrees of freedom, right? So I'm going to go to row 14, and the table only has positive numbers, so we just ignore the negative sign here. Okay, that's why I have you do this check to see if it's positive or negative here, because that's when it would matter. But because it's only the positive side, we just ignore the negative side. Okay, and so we're going to look up 1.339. Okay, ignore the sign once you get to this step. Okay, once you get to this step, you can ignore the sign. So we're going to go to the table, row 14, and we're going to look for 1.339. Okay, so 1.339 would be between what columns?
80 and 90.
It's not between the 80 and 90 column. It would actually be to this side of the 80 column, right? But it's actually not 80. We're going to look at this, the right tail probability. So it would actually be to the left of this column, right? 1.339 is smaller than 1.345, okay? And it's if I had 1.5, it would be between these two columns. But it's not. It's smaller than 1.345, right? So 1.339 is smaller than 1.345, okay? All right, so if, lining it up, 1.339 goes to this side of 1.345. Is that okay? I want to make sure everybody sees that. All I'm doing is I'm just trying to see where the number belongs, okay? And it belongs on this side of the column, okay? And so our p-value belongs on this side of our column heading, okay? If it was over here, then it would go over here. But so my p-value belongs on this side of this column heading. Is that okay? All right. And so here I use, see these t's and they have these little numbers? I'm going to use 0.100. Okay, so my p-value is something to 0.100. Okay. And this part weirds people out, but don't be weirded out by it, okay? 1.339 is smaller than 1.345, but notice that these numbers get bigger as we go to the right, okay? It goes 1.345, 1.761, they get bigger as we go to the right, okay? the column headings, if I look at this 0.100 versus 0.050, 0.025, they get smaller as I go to the right. Okay? So in this case, 1.339 is smaller than 1.345, but my p-value would be greater than 0.0100. Okay? We'll do another example. We'll get our practice. I know it feels weird right now, okay? But so my test statistic 1.339 is smaller than this, so my p-value is greater than 0.100. Okay? So this is my p-value. What do I then do with my conclusion? Do I need to double this? No, because I have a I have a less than sign. If I had a not equal sign, then I would double it. Okay, but I have a less than sign, I don't need to double it. Okay, so my p-value is greater than 10%. If I'm assuming alpha is 5%, is my p-value bigger or smaller than 5%? It's bigger than 5%, right? My p-value is bigger than 10% here, 0.100. So my p-value is bigger than 5%, right? So p-value is greater than alpha, you know, if alpha is equal to 0.05. So what do? We do not reject the null hypothesis. And what does that mean in the context of this pizza problem?
We didn't find much of a difference between the sizes.
Yeah. So even though my sample, I looked at 15 pizzas and the average was less than 12 inches, this does not prove that Domino's is cheating me out of pizza, okay? It doesn't mean that the medium is actually less than 12 inches, okay? So we do not have evidence that the average width of a pizza is less than 12 inches. Is that okay? All right, so let's do a little bit more practice. We have a decent amount to cover here. Okay, so let's say you go through the work. You have degrees of freedom equal to 15. I'm sorry? Yeah, this is practice using the t-table. Okay, degrees of freedom is equal to 15, and your test statistic is equal to 2.8. Okay. What is the corresponding, and let's say the alternative is mu is greater than 3.6 or whatever. Okay, so what is the p-value? All right, what do? We look up degrees of freedom equal to 15. And I'm going to look in that row for where 2.8 fits. Okay? So what do I see? I see 2.8 goes in between 2.602 and 2.947. Is that okay? I'm in the row for 15 degrees of freedom. Here, I'll write a horizontal line here. Okay? So in that row, 2.8 is in between these two values. Okay? And so that means my p-value is in between these two column headings. So I would say my p-value is between what? 0.010 and 0.005. Okay? Do I need to double the column headings? No, because my alternative has a greater than sign. Is that okay with everybody? Yes.
Is this 2 p-values or 1 p-value?
It's one p-value, okay, but it's in a range, okay? All I'm saying is I don't know the exact value, but I do know it's more than 0.005, but less than 0.010, okay? All right, how does this compare? Let's assume alpha is 0.05 for all of these problems. Is my p-value bigger or smaller than alpha? It's between 0.010 and 0.005.
Bigger.
It's smaller. It's smaller, right? It's between 1% and 1/2 of 1%. That's definitely smaller than 5%, right? So, you know, I know the numbers look funny, but don't be deceived by the decimals, okay? So the p-value is less than alpha. Yes?
What if alpha fell like in the middle of your p-value range? So
Okay.
it's both below and
That will not happen. That will not happen. With the way the table is structured, okay, it can't happen that way. Okay, you're either going to be on one side or the other side. The only time something could happen is if your test statistic ends up being exactly one of the values in the table. And that's very rare, but it is possible, and it's the only way it could happen. But it's such a rare occurrence, and in that case,
it's not going to happen on our test.
yeah, okay. I'm not going to be mean to you guys like that, all right? All right, let's try another one. Okay, let's say degrees of freedom is 21. Your test statistic is negative 1.6. Your alternative hypothesis is that mu is greater than 15.0. Okay, what is our p-value? Okay, so I know some of you guys want to say, so this was a trick, okay? Notice I have a greater than sign here, and that means I should have positive here, but I have negative, okay? So what does that mean? Okay, so that means, so I don't look up the p-value, I just say do not reject the null hypothesis, okay? Because these do not match. Okay, because those don't match. But let's try this out again. Test statistic is negative 1.6. The alternative, let's say this time has a, oh here, I'll do a not equal sign, not equal to 15.0. Okay, so now what is my p-value?
Between 0.100 and 0.052.
Okay. That's very close, but remember we have a not equal sign, so I've got to double it. Okay? All right. Okay, so let's look at this. So we ignore this negative sign, and I'm going to look up 1.6, and I've got 21 degrees of freedom, right? So 1.6 is in between 1.323 and 1.721, okay? So my p-value is going to be between these column headings, but because I have a not equal sign, I have to double the column headings, right? So not equal sign means double the column headings. Okay, or I mean you can call this your tail area and then double it. Okay, so I've got 0.100 and 0.050, so we double that and we have 0.200 and 0.100, and so now I say my p-value is between 0.200 and 0.100.
You double both of them.
Yeah, you double both. You double your column headings, okay? So in this case, is my p-value bigger or smaller than alpha? Assuming alpha is 0.05? Yeah, so here, my p-value, so if alpha is 0.05, my p-value is greater than alpha. Do not reject the null hypothesis. Okay, let's just do one more, because I still have that last topic to cover, right? Okay, so the last one, let's say degrees of freedom is equal to 9. Your test statistic ends up being 7.4, and your alternative is that mu is greater than whatever, 2.1. What's our p-value? Okay, so I'm going to go to 9 degrees of freedom, and I look in this row, and I see, where does 7.4 fit? 7.4 is larger than the last number here. It's larger than 4.297. Okay, so here, my p-value is going to be more or less than 0.001. Less than, because I'm going further away from 0. So I don't need to double it because I've got a greater than sign here. So my p-value is less than 0.001. Okay? And so if alpha is 0.05, what do we do? Is my p-value bigger or smaller than alpha? P-value is smaller than alpha, so we reject the null hypothesis. Okay. I know it feels odd, okay, the first time you're using the t-table, okay? But just like anything, everything in life, the first time you try something out, or the first few times you try something out, it feels a little strange, but you'll get used to it, okay? With practice, right? Okay, so our last topic, hypothesis testing for means and 2 samples. Okay, and if you need to review that part of the video, you can review it. Means 2 samples. Okay, this is very similar to hypothesis testing for proportions with 2 samples. This time it's means. Okay, so the null hypothesis is always mu1 equal to mu2, or it can also be written as mu1 minus mu2 equals 0. Okay, this is always the null hypothesis. The alternative will be then mu1 not equal to mu2 or greater than or less than, okay? Or same parallels over here. The test statistic is going to be x bar 1 minus x bar 2 divided by the standard error, and the standard error is the square root of s1 squared over n1 plus s2 squared over n2. Okay, you look this up. Look up test statistic in the t-table to get your p-value. Okay, done exactly the same way as you did the t-table for p-values when you had one sample in means. Okay, and your degrees of freedom is equal to n minus 1 using the smaller of n1 and n2. It all kind of makes sense, right? Putting everything together, right? What you understand about hypothesis testing for, I know it's 9:50 and you know by now your brain is a little bit mush, but you look at how we did hypothesis testing in confidence intervals for proportions, and you can see that it's very similar when we're doing with means. It's just kind of our formulas have changed, but the reasoning is all the same, okay? And then you look this up, and then with the p-value, you make your conclusion. Exactly the same as before, okay? How does this feel? Okay. I don't think we need to get into do a full-blown example here, okay? You have examples in your homework, examples on the practice quiz, okay? I think we'll wrap it up there for the evening. We'll see you guys next week, okay?